In the beginning, there was no Sunday, no planets, no moons, no gentle arcs of orbit. There was only a drifting sea of darkness, filled with the quiet breath of ancient stars. Their ashes, scattered by explosions so distant in time that even galaxies had forgotten their names, floated through the void like dust suspended in a cosmic cathedral. This was the solar nebula, vast, cold, and dreaming. Its memories stretched back billions of years. Each grain of dust carried the history of a star that had lived and died long before our sun existed. Iron from a collapsing giant, silicates forged in the heat of distant suns, carbon shaped in the quiet burning of red dwarfs, even traces of gold and uranium, rare whispers of violent supernovae rested within this cloud. Nothing in the nebula was still. Though it appeared serene, every particle was in motion, drifting, colliding, separating, waiting. The nebula's edges stretched across light years, thin as breath. In some regions, its fog-like swirls were barely distinguishable from the vacuum around them. In others, clumps of material thickened into strands like celestial spider silk. And at the heart of this enormous cloud, something subtle began. A disturbance, small at first, unnoticed by the ancient dust. Perhaps it was the passing of a nearby star whose gravity tugged the cloud. Perhaps it was the shockwave of a long-forgotten supernova. Or perhaps it was simply time, nudging the nebula toward the moment it had waited for since the universe was young. Whatever the cause, the calm began to break. Particles drifted inward. The cloud stirred. Gravity silent, patient, inevitable woke from its long slumber. At first, the collapse was gentle, like a breath being drawn. The nebula contracted slowly, gathering mass toward its center. Every atom answered gravity's call. Hydrogen, simple, ancient, the universe's first element, became the foundation of what was coming. As the collapse continued, movement accelerated. What was once a diffuse cloud began to rotate, pulled into a great swirling disk. The more it spun, the flatter it became, like a whirlpool forming on a cosmic scale. This was the protoplanetary disk, the cradle in which everything we know, every planet, every moon, every grain of cometary ice, would eventually be sculpted. At the core of this disk, heat began to gather. The pressure of falling material compressed the central region. Energies released from collisions built upon each other. Hydrogen atoms, once floating aimlessly, were forced closer and closer together until they trembled with the effort of resisting fusion. The nebula brightened from within. Not yet a star, but no longer a cloud. Around this growing core, the disk continued to spin. Dust grains collided and stuck together, forming larger clumps. Static charges, van der Waals forces, and gentle gravitational pulls helped them cling. Pebbles formed, then boulders, then kilometer-wide planetesimals, rough, irregular bodies that would one day become worlds. But in these early moments, everything was wild, chaotic, violent. Planetesimals crashed into each other, exploding into fragments that would later reassemble. Entire regions of the disk glowed with heat from countless impacts, like sparks in a windstorm. Yet amid the chaos, an undeniable pattern was forming. The nebula's memory, old as the stars themselves, guided the disk toward order. At the center, the growing protostar continued to gain mass. Its interior heated further, pushing hydrogen atoms toward the threshold where fusion might ignite. The entire disk revolved around this gathering flame, pulled forward by momentum and inward by gravity. There were moments, if moments can exist in cosmic time, when the nebula seemed to hesitate, as if deciding whether this collapse was meant to produce a star or become another forgotten cloud drifting between constellations. But the decision had already been made. The protostar brightened. Pressure built, and somewhere deep within that forming core, The first whispers of nuclear fusion flickered. Hydrogen fused into helium. Light, real light, burst forth. Not the faint, reflected glow of distant suns, but the beginning of a new star's own fire. The primordial nebula trembled. Its long-held silence was broken. Around the newborn star, the disk shone like a great cosmic halo. Heat surged outward, pushing volatile materials to the outer regions, while heavier elements remained near the center. The architecture of the future solar system began to emerge. Inner regions, warmed by the new star, would one day form rocky planets. Outer regions, colder and calmer, would gather into giants of gas and ice. And far beyond, at the edge of the fading nebula, icy grains would remain untouched, preserving memory from the earliest days of the universe. Everything that would ever exist in this solar system, oceans, volcanoes, mountains, atmospheres, continents, and even life, began here, in this swirling disk of dust and dreams. If you could stand within the nebula at that moment, you would see churning clouds of glowing particles drifting in soft, slow spirals. You would feel heat building at the core. You would sense movement in every direction, like the whisper of wings in a vast chamber. You would not yet see planets. You would not yet see the sun as you know it. But you would feel the inevitability of their coming, for this was the birthplace of everything. The first heartbeat of the solar system, the earliest memory the universe chose to preserve, long before Earth formed oceans, long before Jupiter gathered storms, long before Pluto wandered in darkness, there was a cloud, ancient, quiet, waiting to become something more. And from that quiet beginning, the solar system opened its eyes. In the heart of the collapsing nebula, the protostar continued to gather strength. It was not yet the sun, not the warm, familiar presence that would someday guide the rhythms of Earth, but a dense, glowing sphere hidden within a cocoon of dust. Its light was faint, diffused through swirling clouds that softened every flicker. But its heartbeat had already begun. Gravity pulled relentlessly inward. The protostar fed on the surrounding nebula like an ember consuming dry leaves. Every particle that drifted too close surrendered its energy to the growing core. Heat built in layers, spreading outward in waves that rippled across the forming system. The young star quivered under the pressure, not yet stable, but too massive to remain silent. Inside its core, hydrogen atoms were pushed together with unimaginable force. They trembled, resisted, then broke apart, only to fuse again into helium. In that moment, so brief compared to cosmic time, nuclear fusion ignited fully. Light was born. Not borrowed light, not reflected light, but its own brilliant, radiant flame. The cocoon of dust surrounding the protostar glowed from within like a lantern held behind a veil. The solar wind, a steady stream of charged particles, swept outward in all directions. For the first time, the forming solar system felt the breath of its central star. The protostar had become the Sunday, and the sun remembered its birth. It remembered the crushing weight of the nebula folding inward. It remembered the moment heat overwhelmed darkness. It remembered the first pulse of fusion, like a spark catching in a long dormant furnace. But the newborn sun was restless. Fusion surged unevenly. Its surface roiled with flares, magnetic storms, and eruptions that hurled plasma deep into the protoplanetary disk. The star spun faster than it ever would again, its magnetic field twisting like coiled threads of fire. These storms were not destructive, they were formative. Each burst of radiation carved the disk, sculpting lanes of dust and gas. Lighter particles were pushed outward, heavier ones drifted inward. Clearings opened, where future planets would circle. The sun watched its first children taking shape, though they were only clusters of planetesimals colliding in chaos. At this stage, The sun was not the gentle star humanity would one day admire in pastel sunsets and warm summer mornings. It was a roaring infant, brilliant, unpredictable, and powerful. Its brightness was nearly 1/3 weaker than today's, but its temper was far greater. Solar flares erupted like cosmic lightning, illuminating the swirling disk with flashes of incandescent fire. Despite the turbulence, the sun's light began to claim territory. The warmth spread across the innermost region of the disk, evaporating volatile ices and leaving behind only metals and silicates. This region, harsh and bright, would become the birthplace of Mercury, Venus, Earth, and Mars. Farther out, where the sun's heat softened into a gentle glow, gases and ices remained intact. There, the seeds of giant planets stirred. The sun's role was more than illumination, it was architecture. Its gravity shaped the orbits of everything. Its heat defined what materials could survive. Its wind swept clean the inner system, blowing away the leftover gas and dust that had not yet coalesced into worlds. Every newborn solar system in the galaxy experienced these same steps, but the sun's story carried its own quiet signature, a distinct rhythm etched in plasma and memory. The young star spun, glowing ever brighter. The fusion in its core stabilized. Hydrogen fused into helium at a steady rate. Pressure balanced gravity. The sun found its equilibrium, a delicate dance of forces that would last for billions of years. It was only a few million years old, an infant in stellar terms, but already it held the promise of stability, a rare, precious trait in the restless cosmos. With time, the sun cleared the remaining fog of its birth cloud. The nebula that once surrounded it dispersed into space, revealing a star burning alone at the center of its disk. The darkness no longer smothered its light. The sun shone freely, illuminating bodies still too small to be called planets. And in the glow of this light, the disk transformed again. Temperature gradients sharpened. Pressure waves rippled outward. Dust aligned along subtle gravitational lanes, as if the sun were whispering instructions to the material orbiting it. In the warmth of the inner disk, tiny grains melted and solidified into chondrules, sparkling beads of rock that would one day be preserved in meteorites. These chondrules drifted, collided, and fused into larger rocks. Those rocks formed clusters. The clusters gathered into embryos of future worlds. The sun watched this with ancient patience, though it had only just been born. It understood what these motions meant. It had witnessed such processes countless times in the long cosmic cycles of star birth. But this disk, this family, it would remember differently. For the sun felt something that stars do not often feel: continuity, because in its heart, built from the ashes of older stars, were elements that had once belonged to other stellar families, other planets, other children of light. This new system was not isolated. It was part of a lineage stretching back to the earliest days of the universe. As the sun matured, the last remnants of its birth cloud faded into distant space. What remained was a brilliant young star surrounded by a swirling orchestra of matter, an orchestra tuning itself for the long symphony of planetary formation. The first true sunrise had not yet occurred. No planet existed with a surface to receive it, but the light was there, waiting, searching, filling space with warmth and promise. The sun's memory of its birth became the foundation of the solar system's identity, a memory etched in every orbit, every beam of light, every comet that traces a long, elliptical path through the darkness. From this moment on, the sun would burn steadily, faithfully, patiently. For billions of years, it would shine on worlds that did not yet exist. It would ignite atmospheres, nourish oceans, and awaken life. It would guide seasons, sculpt climates, and bear witness to civilizations rising and falling. All of that lay far, far in the future. For now, the sun simply existed, newborn yet ancient, powerful yet peaceful, holding in its light the first true memory of the solar system. And the planets, not yet formed, drifted in the disk, waiting for their turn to awaken. As the sun settled into its newborn brilliance, the swirling disk around it began to change. Heat radiated outward, shaping the inner region into a crucible where metals and silicates dominated. Here, within this bright and turbulent zone, the foundations of 4 future worlds were quietly forming. At first, there were no planets, only dust, drifting stones, and fragments of material that collided constantly. Every impact released heat. Every collision changed the destiny of the fragments involved. Some shattered into dust, others merged into larger bodies. Slowly, steadily, the inner disk transformed from chaos into architecture. These early building blocks, called planetesimals, were irregular, jagged, and fragile. They drifted along curved paths, guided by gravity and sunlight. When two collided gently, they stuck. When they collided violently, they shattered. But the overall trend was unmistakable: growth. Neighborhoods of dust became clusters of stones. Clusters became boulders. Boulders became mountain-sized bodies. And from these, the first protoplanets were born. The sun watched this process with a quiet, ancient patience. It knew that from this swirling haze, worlds would emerge, each with its own character, its own future, its own memory. Mercury, the scorched remnant, closest to the sun, where heat was merciless, the proto-Mercury formed from the most resilient materials. The newborn world grew dense and metallic, its iron core dominating its structure. Violent collisions stripped away much of its rocky mantle, leaving behind a world that was smaller than it had once been, yet incredibly heavy for its size. Mercury remembered every blow. Its surface bore the craters of ancient impacts, rings within rings, scars upon scars. It was a world shaped by fire and violence, destined to orbit nearest the sun for billions of years, enduring temperatures that would melt metal in moments. Venus, the lost twin. Farther out, another protoplanet grew a world rich in rock and metal, heavy with possibility. It spun more slowly than its neighbors, perhaps due to a titanic collision that reversed its rotation. For a time, Venus was gentle. It possessed oceans of liquid water and temperatures that allowed chemical dances across its surface. But something shifted. Its thickening atmosphere trapped heat relentlessly, turning gentle warmth into suffocating fire. Volcanoes erupted ceaselessly. Pressure mounted. Water vanished. Venus became a memory of what might have been, a twin of Earth, lost to runaway heat. Earth, the lucky one. Amid the unfolding drama, the proto-Earth grew from countless collisions. For every fragment that joined its body, Earth remembered the energy, absorbing momentum and mass. Gravity strengthened. The surface melted into oceans of magma before cooling slowly, forming a thin crust. Earth was neither too hot nor too cold. It lived in a rare zone, the habitable zone, where water could remain liquid and chemistry could explore endless possibilities. But Earth's early nights were dark. The moon did not yet exist. Its rotation was rapid. Its surface was still molten. Earth was young, fragile, and unfinished. Soon, a titanic event would change everything. Mars, the smaller dream. Beyond Earth, the proto-Mars grew quickly at first. It had access to rich materials, and for a time, it flourished, becoming nearly half the size it needed to be to sustain long-term geological activity. But Jupiter's immense gravity interfered. Planetary embryos competing with Mars were flung away or prevented from merging. Mars stopped growing early, too early. Still, Mars carried the memory of its youth. Rivers carved into its surface, volcanoes that pierced the sky, lakes that glimmered beneath its hazy atmosphere. It would one day become a frozen desert, but in these earliest moments, it was full of promise. The dance of embryos. The inner solar system was not peaceful during these formative ages. Dozens of planetary embryos roamed the region, each a contender for becoming a full-sized world. They collided, merged, and shattered in unpredictable cycles. Some grew into Mercury, Venus, Earth, and Mars. Others were destroyed. Still others were ejected toward the outer solar system or lost to the Sunday. This chaotic ballet lasted tens of millions of years, but gradually the orbits stabilized. 4 worlds remained, where once there had been dozens. Their shapes became round under the pressure of gravity. Their surfaces cooled, forming crusts that preserved the earliest scars. Each new world held a different memory of its birth. Mercury remembered heat and violence. Venus remembered balance, turned to catastrophe. Earth remembered warmth and possibility. Mars remembered growth interrupted, the sun's guiding hand. Throughout this era, the sun shaped everything. Its heat determined what materials could survive in the inner disk. Its gravity synchronized the orbits of the growing planets. Its radiation drove away the excess gas and dust, leaving behind only what could cling tightly. The sun did not control the planets directly, but like a conductor guiding a symphony, it nudged them toward harmony. Eventually, the inner disk thinned. The worst of the chaos ended. The collisions that once defined the region grew rare. In this newfound calm, the 4 rocky worlds began their long evolution. They were young and imperfect, their surfaces scarred and unstable, but they had survived the crucible of creation. The solar system's memory now included its first family of planets, each beginning to write its own story, each preparing for the next dramatic chapter that would shape their destinies. The inner worlds had been born. Soon, the moon would rise, oceans would form, atmospheres would shift, and life, on one world, would begin its improbable journey. But for now, in this early epoch, the solar system simply rested, as 4 rocky worlds circled their newborn sun, carrying within them the deep memories of fire, impact, and creation. Before the moon existed, Earth was a restless young world, hot, molten, and spinning rapidly under the glow of a turbulent Sunday. Its sky was filled not with the calm blue we know today, but with swirling clouds of steam and volcanic gases. The surface shifted constantly, reshaped by violent impacts as leftover debris from planetary formations swept across the inner solar system. The early Earth was not yet complete. It lacked the quiet rhythm of tides. It lacked the steady tilt that would one day define its seasons. And above all, it lacked the companion that would shape its entire future, the moon. The moon was not born gently. Its origin was an act of unimaginable violence, a collision so catastrophic it nearly destroyed Earth, yet so precise that it ultimately gave rise to the world we now know. The arrival of Theia, as Earth grew, another planetary embryo formed nearby. Both circled the sun on similar paths, their orbits weaving closer together over millions of years. This sibling world, roughly the size of Mars, is known today as Theia. Theia had its own history, its own accretion of rock and metal, its own molten core and youthful energy. For a time, Earth and Theia coexisted peacefully, each following its path around the Sunday. But the inner solar system was still crowded with planetary fragments, and gravitational nudges slowly destabilized Theia's orbit. One day, a day that would define the next 4.5 billion years, Theia and Earth crossed paths. Scientists believe the impact was not head-on, but a glancing collision, the kind that transfers enormous energy without obliterating both bodies completely. But even a glancing impact between worlds was almost beyond comprehension in scale. The collision that changed everything. The moment Theia struck Earth, the solar system burned with light, Shockwaves tore across Earth's mantle. Mountains vaporized instantly. Oceans of magma were thrown into space. Theia's crust shattered. Its core plunged deep into Earth, merging with Earth's young metallic heart. The energy released was greater than that of 1,000,000 trillion nuclear explosions. Earth's rotation changed. Its axis tilted. Its surface melted again into a global ocean of fire. Debris, molten rock, metal fragments, vaporized minerals shot into orbit around Earth, forming a glowing ring of incandescent material. This ring would not last long, but for a brief period it encircled Earth like a halo of fire, a reminder of the chaos that had reshaped the planet. Within this ring lay the seeds of the moon, the gathering of the moon. At first, the debris was a storm of fragments, droplets of magma cooling in space, chunks of crust, and swirling plumes of silicate vapor. But gravity began its gentle, inevitable work. Slowly, the fragments clumped together. Clusters merged into larger bodies. These bodies attracted more material, growing with each collision. In the silence of space, a new world began to take shape. The forming moon orbited close, very close to the young Earth, so close that it would have filled much of the sky, appearing dozens of times larger than it does today. Its early orbit was fast and tight, its gravitational pull fierce. The moon was still molten at first, its surface glowing red, its core churning with leftover heat from its violent birth. But as it cooled, craters formed from the last waves of debris that continued to rain down. Large seas of basalt spread across its young surface as volcanic activity reshaped the plains. The moon evolved quickly compared to Earth. It became geologically quiet, preserving the scars of its origin like a fossil in space. Earth transformed. The impact changed Earth forever. Earth gained a larger metallic core. Theia's core merged with Earth's, enriching Earth's interior with iron and helping generate the strong magnetic field that shields our planet to this day. Earth's tilt stabilized. Before the impact, Earth's axis may have wobbled unpredictably. Afterward, with the moon acting as a stabilizing partner, Earth's tilt settled into a steady 23.5 degrees, giving rise to predictable seasons, climate cycles, and environmental rhythm. Day length increased. The impact slowed Earth's rotation. What may once have been a 5-hour day lengthened toward the 24-hour cycle we know now. Over billions of years, the moon's pull would continue to slow Earth's spin, drawing ever farther away. Tides emerged. With the moon came the tides, the steady pulse of oceans that would later influence coastal life, nutrient cycles, and perhaps even the earliest steps of organisms onto land. Earth's crust changed composition. The moon-forming impact mixed Earth's outer layers, setting the stage for plate tectonics, volcanic outgassing, and the conditions that would eventually create atmosphere and oceans. Earth was wounded, but through that wound came transformation. The chaos of the impact laid the foundation for stability, diversity, and life. The long goodbye of Theia. In a sense, Theia did not vanish. Its remnants live on in Earth's core, in the moon's rocks, and perhaps within deep layers of Earth's mantle. The moon itself may be half Earth, half Theia, a shared monument to catastrophic creation. Every time you look at the moon, you are seeing the ghost of Theia, preserved in pale stone, orbiting gently above the world it helped shape. A new sky. As Earth cooled after the impact, the molten crust began to solidify again. Steam condensed into rain that fell for thousands of years, forming the first oceans. Volcanoes roared, releasing gases that would become the early atmosphere. And above this raw, reshaping world hung the newborn moon. It shone far brighter than it does today. Its surface still warm, its orbit much tighter. It pulled at Earth's oceans with immense force, creating tides that were hundreds of times stronger than those we see now. Night on early Earth was no longer dark. The moon dominated the sky, a glowing guardian watching over a world struggling to rebuild itself. The memory of the moon. The Earth-Moon system became a partnership unlike any other in the solar system. Most planets do not have moons of this size. Most impacts destroy worlds rather than remake them. But Earth and Theia created something rare, something stable, something beautiful. A double world. A mother and child locked in gravitational embrace. A system that would nurture life, weather, climate, and the slow unfolding of billions of years. The moon became Earth's memory. Its surface recorded the history that Earth would later erase through oceans, erosion, and plate tectonics. While Earth changed constantly, the moon remained still, preserving the ancient scars of its birth. Together, they moved forward, two worlds bound by one violent moment, shaping each other for all time. In the aftermath of the moon-forming impact, Earth was a world reborn through fire. Its entire surface had melted into a global ocean of magma, a restless, glowing sea stretching from horizon to horizon. Volcanoes burst from the molten crust like sparks from a furnace. Ash and vapor rose into a sky that shimmered with heat. There were no continents, no oceans of water, no atmosphere as we know it. Earth was still shaping itself, still gathering the strength it would need to host life. This young world was violent, but within its chaos, the seeds of stability were quietly forming. The long cooling. Earth's molten surface radiated heat into space. For millions of years, the planet cooled slowly, like an iron sphere left outside in the night. But the cooling was uneven. Some regions solidified faster, forming patches of crust that cracked and sank again into the magma. Above the glowing surface, the atmosphere churned. Steam billowed from volcanoes. Gases such as carbon dioxide, sulfur dioxide, nitrogen, and water vapor thickened the sky, trapping heat and preventing complete cooling. Yet slowly, steadily, Earth's temperature decreased. The magma ocean began to harden. The crust thickened enough to survive the constant impacts of leftover debris circling the Sunday. Each impact reheated the surface, but fewer and fewer struck as the early solar system grew calmer. The first crust was dark, volcanic, and unstable, a thin skin stretched over a restless interior, the sky of endless rain. As Earth cooled, water vapor in the atmosphere condensed. Clouds gathered, thick and heavy. For the first time, rain began to fall. It did not fall gently. This was no ordinary rainstorm. For thousands, perhaps millions of years, rain poured in unbroken torrents. Not drops, but continuous sheets of water hammered the crust. Lightning cracked across the sky. Steam rose in vast clouds when raindrops hit hot rock. The sound must have been deafening, a world wrapped in endless storms. As the storms continued, Earth transformed again. Water, collected in low basins, pools, became lakes. Lakes became oceans. Bit by bit, the first true bodies of water spread across the planet's surface, cooling the crust further and shaping the landscape that would one day host continents. Earth was no longer just fire. It was becoming a planet of water, the breath of volcanoes. While rain built oceans from above, volcanoes continued to shape Earth from below. Volcanic outgassing released enormous quantities of water vapor, carbon dioxide, ammonia, methane, and other gases. These built the early atmosphere dense, warm, and alien. There was no oxygen yet. The air was toxic to the life forms that would evolve billions of years later. But this atmosphere was essential. It trapped enough heat to keep the oceans from freezing entirely. It sheltered the surface from meteoritic bombardment. It helped transport heat around the planet. Earth breathed through its volcanoes, exhaling the materials that would one day nourish life. The formation of the first crust. The crust thickened as magma cooled. Volcanoes rose and fell as pressure built beneath them. Over time, the first stable pieces of continental crust emerged. These early continents, called cratons, were small and scattered, islands in a global ocean. Their rocks were light, buoyant, and resistant to sinking back into the mantle. Because of this, some of the oldest rocks on Earth, more than 4 billion years old, still exist within these ancient cratons today. The continents were shaped by the movement of the mantle beneath them. Earth had begun its slow dance of plate tectonics, a process that would recycle crust, build mountains, and create the dynamic surface we see today. The memory of these first continents remains locked in minerals older than any life form. The first oceans settle. As rainfall lessened and temperatures stabilized, the world entered a new phase. The oceans quieted. Cloud cover thinned. Steam no longer obscured the sky entirely. Occasional breaks in the clouds may have allowed faint starlight to reach the surface for the first time. The early oceans were warm, mineral-rich, and restless. Hydrothermal vents on the ocean floor spewed hot, chemical-rich water. These vents created environments unlike anything visible on the surface, dark, pressurized, yet full of the building blocks of chemistry. In these deep, shadowed pockets, life's first ingredients would one day gather, but in this era, life was still only a possibility, a concept carried in the atoms and molecules swirling in the sea. The calm after chaos. As volcanic activity slowed and impacts grew rare, Earth's environment stabilized into something remarkably balanced. Warm oceans covered most of the surface. A thick atmosphere shielded the planet. The moon had moved outward enough to calm Earth's wobble, creating predictable tides. Heat from the interior fueled plate tectonics, shaping the crust. Sunlight, now steady and consistent, began to reach the surface more clearly. Earth had shifted from a world of destruction to a world of possibility. For the first time, conditions were suitable for complex chemistry to unfold in the oceans. Not yet life, but the precursors of life. A new kind of memory was forming, not shaped by fire or stone, but by molecules finding patterns. A planet preparing for life. Earth in this era was a place of contrasts. Violent storms, paired with calming oceans. Molten interiors beneath a cooling crust. Toxic atmosphere above waters full of potential. But it was precisely these contrasts that created the diversity needed for life to emerge. Lightning struck the oceans, sparking chemical reactions. Minerals from volcanic rock dissolved into the water, enriching it with nutrients. Hydrothermal vents injected energy into dark ocean floors. Everything was in motion. Everything was changing. Everything was ready. Earth, once a molten sphere battered by cosmic violence, had become a world with oceans, continents, atmosphere, and stability. A world poised for the next great chapter. Life would not appear immediately. It would take hundreds of millions of years. But the stage was set. The age of fire had given way to the age of water, and the age of life was waiting quietly beyond the horizon. Before Venus became a furnace of storms and sulfur, it was a world full of promise, a world not so different from Earth, a world that might have been blue, calm, and alive. But memory is fragile in the solar system, and Venus carries a memory shaped by tragedy, a gentle beginning, followed by a collapse so complete that it transformed the planet forever. A sister born beside Earth. As the sun's heat sculpted the inner solar system, Venus took shape in a region just slightly closer to the star than Earth. It grew from the same swirling disk of dust and rock, collecting heavy metals and silicates as it formed. The proto-Venus glowed red, molten, and restless, wrapped in a thick haze of volcanic gas. But as its surface cooled, Venus entered a phase eerily similar to Earth's. The crust solidified. Volcanoes exhaled steam and carbon dioxide. Oceans of water vapor condensed in the skies. Temperatures dropped enough for the first hints of stability to emerge. If you could have stood on Venus during this early time, you might have seen something astonishing. Clouds of water drifting across a dim orange sky, volcanic highlands rising above plains of cooling rock, and sunlight filtering through in soft, muted rays. The two worlds, Earth and Venus, were twins in almost every way, nearly identical in size, nearly identical in mass, nearly identical in composition. Their early histories seemed destined to run parallel. But something subtle was already shifting. The slow turn toward catastrophe. Venus received just slightly more sunlight than Earth, a difference Earth could have survived. But Venus could not. Water vapor, a powerful greenhouse gas, trapped more heat in the atmosphere. As surface temperatures rose, more water evaporated from early Venusian seas. This, in turn, trapped even more heat. A brutal feedback loop had begun. On Earth, the oceans remained stable. On Venus, they started to boil. The atmosphere thickened. Clouds of steam grew denser. Volcanoes erupted relentlessly, releasing more gases into the air. Carbon dioxide accumulated faster than it could be removed. Venus was walking a narrow line, and it began to slip. The disappearance of the seas. As temperatures climbed past the boiling point of water, Venus's oceans vanished into the sky. Steam filled the atmosphere, stretching high into the upper layers where solar radiation tore water molecules apart. Hydrogen escaped into space. Oxygen reacted with the surface and vanished into the rocks. The planet lost its water forever. Without oceans to absorb carbon dioxide or regulate temperature, greenhouse heat intensified catastrophically. Venus entered a runaway phase that accelerated with terrifying speed. It was no longer becoming warm. It was becoming hell. The reinvention of Venus. As steam cleared, Venus was left with a planet-sized desert of rock, hotter than molten lead. The atmosphere thickened into a crushing blanket of carbon dioxide, more than 90 times the pressure of Earth's. Sulfur dioxide formed clouds of sulfuric acid that wrapped the planet in a permanent yellow haze. Lightning crackled through the dense atmosphere, illuminating storms that raged with unimaginable power. Winds screamed across the upper clouds at hundreds of kilometers per hour, while the surface remained nearly windless under the oppressive weight of the air. Volcanoes reshaped the landscape again and again. Entire regions were resurfaced. Lava plains stretched across millions of square kilometers. Some scientists believe Venus experienced global volcanic events, periods where most of the crust melted and refroze. The gentle world Venus might have been was gone. In its place stood a monument to instability. Yet memory lingers in the rocks, and atmosphere clues hinting that Venus once stood at the edge of habitability. The planet that rotates backwards. Venus rotates in a way unlike any other major planet. It spins backwards. A day on Venus, one full rotation lasts 243 Earth days. A Venusian day is longer than its year. Why? Two possibilities remain. A massive early collision may have flipped Venus over on its axis. Atmospheric tides may have gradually slowed the rotation until it reversed. Either way, this strange rotation contributed to temperature extremes. Without rapid rotation, Venus could not distribute heat evenly. The same regions faced the sun for weeks at a time, further destabilizing climate. Even in motion, Venus kept choosing paths that led toward catastrophe. The locked memory of the atmosphere. Venus's atmosphere became a vault sealed, suffocating, and unforgiving. No rain reaches the surface. Clouds reflect sunlight, but trap infrared heat with brutal efficiency. The air is so dense that standing on Venus would feel like being nearly a kilometer underwater on Earth. Temperatures near 475 degrees Celsius, 900 degrees Fahrenheit, melt lead, zinc, and tin effortlessly. The atmosphere preserves Venus's past, the way amber preserves ancient insects. Every molecule tells a story of oceans lost, heat trapped, and chemistry spiraling out of balance. A lesson written in fire. Of all the worlds in the solar system, Venus is the one that reminds Earth how fragile habitability can be. Two worlds began almost the same. One became a cradle for life. The other became a furnace. Venus is not simply a failed Earth. It is a warning of how small differences in distance, rotation, or chemistry can rewrite an entire planetary destiny. The Venus that might have been. Some scientists believe Venus may once have had shallow oceans, a mild climate, temperate skies, potential for early life. If Venus had drifted slightly farther from the Sun, it might have remained Earth-like. If its rotation had not reversed, it might have stabilized. If volcanic outgassing had been slower, water might have remained, but history chose differently. Venus, the bright star of the morning and evening sky, is a world defined by lost potential, a memory of what happens when a planet crosses the line between balance and collapse. A silent twin under the clouds. Today, Venus hides its surface beneath thick clouds, refusing to reveal its secrets easily. But radar mapping has shown mountains, plains, volcanic domes, and canyons deeper than Earth's. Beneath the suffocating atmosphere lies a silent world of rock, preserved as if frozen in heat. A world once full of promise. A world that diverged from its twin. A world that teaches us what it means for a planet to remember both what it was and what it lost. Before Mercury became the scorched, cratered world we know today, it was a child of extremes, formed in the brightest, hottest region of the early solar system. Its story is one of survival through imbalance, of becoming dense where others became wide, of withstanding the sun's furnace while carrying secrets deep within its metallic heart. Mercury was never meant to be gentle. Its memory is written in fire and shadow. Born in the inner crucible, when the inner solar nebula began to condense, the region closest to the sun became a harsh arena. Temperatures soared high enough to vaporize lighter elements. Only the heaviest materials, iron, nickel, metal-rich silicates, could survive long enough to clump into solid bodies. This was Mercury's cradle, a place where rock melted, metal condensed, and dust glowed before cooling. As planetesimals collided and merged, Mercury took shape as a dense, compact world with a disproportionately large iron core. From the beginning, it was more metal than stone, more weight than size. Even among its siblings, Mercury was unique, the collision that stripped a world. One of the enduring mysteries of Mercury is why it has such a massive core, making up nearly 85% of its interior, far higher than any other terrestrial planet. The leading theory tells a dramatic tale, a giant impact. A young proto-Mercury larger than the world we see today may have been struck by another massive embryo early in its life. The collision would have blasted away much of Mercury's rocky mantle, left its iron core largely intact, reshaped the planet into its current compact form. This explains why Mercury is the smallest terrestrial planet, yet among the densest. It is a world reduced to its essentials, like a gemstone cut from violent pressure, locked between fire and ice. Mercury orbits so close to the Sun that its days are blistering, while its nights plunge toward absolute cold. At noon, temperatures soar above 430 degrees Celsius, 800 degrees Fahrenheit. At night, without atmosphere to retain heat, they drop below 280 degrees Celsius, 290 degrees Fahrenheit. Such extremes would shatter most worlds. But Mercury endures them silently, like an ancient artifact exposed to a cosmic forge. Its surface is an archive of impacts, vast basins, long scarps, and craters packed together in a density unmatched in the inner system. The formation of Caloris Basin. Of all Mercury's scars, none is more striking than Caloris Basin, one of the largest impact structures in the solar system. It was forged by a colossal collision that released energy equivalent to billions of nuclear bombs. Molten rock splashed outward, creating rings of mountains more than a kilometer tall. On the opposite side of the planet, at the exact antipode of the impact, the blast waves converged, fracturing the crust into a chaotic terrain of ridges and cliffs. This is Mercury's memory, printed into stone. Violence, recorded on a planetary scale. A magnetic field against all odds. Despite its small size and nearly airless surface, Mercury possesses something unexpected: a global magnetic field. Most planets, its size would have cooled internally long ago, their cores solidifying, their magnetic fields dying out. But Mercury's massive iron heart remains partly molten, generating a magnetic field only 1% as strong as Earth's, yet still remarkable for a world so small. How does Mercury keep its core active? There are several possibilities: residual heat from formation, radioactive decay in the interior, unusual sulfur content lowering the core's melting point, tidal forces from the sun keeping the interior stirred. Whatever the cause, Mercury's magnetic heartbeat continues, faint but steady. The mysterious hollows. One of the strangest features discovered on Mercury by the Messenger spacecraft is the presence of hollows, bright, shallow depressions with no clear earthly equivalent. They appear young, formed by volatile materials evaporating from the crust under the harsh solar heat. These hollows shimmer with fresh brightness, suggesting Mercury is still geologically active in subtle ways. Even near the sun's furnace, Mercury finds ways to change, to adapt, to surprise. A world of long shadows. Because Mercury rotates slowly, once every 59 Earth days, its dawn and dusk stretch for weeks. Shadows creep across craters with glacial patience. Inside deep polar craters, sunlight never reaches the floor, creating pockets of eternal darkness where ice has persisted for billions of years. Ice on Mercury may seem impossible, yet it endures. Comets that struck the poles deposited frozen water, which became trapped in the cold shadows, shielded from the sun's heat. Even in the hottest region of the solar system, Mercury carries the memory of ice, the strange 3-2 resonance. Mercury does not spin freely. Its rotation is locked in a rare resonance with its orbit. Mercury rotates 3 times. For every 2 revolutions around the Sun, this 3-2 resonance keeps certain regions exposed to the Sun repeatedly while others remain sheltered. It creates predictable cycles of heat and shadow, a planetary rhythm shaped by gravity and proximity. This pattern allowed some early astronomers to mistakenly believe one side of Mercury always faced the Sunday. In truth, Mercury is more subtle, its dance more complex, the quiet world with a loud past. Today, Mercury is quiet. It has no weather, no atmosphere to stir winds or clouds, but its stillness hides a history more dramatic than many larger worlds, forged in fierce heat, carved by early collisions, stripped nearly to its core, beaten by impacts, scarred by heat and frozen night, yet still holding ice, still generating a magnetic field, still orbiting in the most extreme environment in the inner system. Mercury is the solar system's survivor, a world of contradictions, small yet dense, scorched yet icy, silent yet full of buried activity, a memory of what the inner system once was. Mercury carries the oldest, least altered surface among the terrestrial planets. Where Earth reshaped itself through oceans and tectonics, Venus through heat, and Mars through erosion, Mercury remained a witness. Its craters preserve the story of the early bombardment. Its cliffs mark the shrinking of a cooling planet. Its core remembers the violence that stripped its mantle. Its ice preserves the subtle gifts of far-traveling comets. Mercury is more than a small world next to the Sun. It is the inner solar system's ancient journal, a record written in metal and stone, an artifact of the earliest chapter of planetary creation. And though it does not speak, its silence is full of memory. Long before Mars became the silent, red desert we know today, it was a world filled with movement and sound. A world with rushing rivers, echoing canyons, rising volcanoes, and a sky touched by clouds. It was not Earth's shadow. It was Earth's younger sibling, bold and full of potential. Mars carries this memory deep within its rust-colored stones, a memory of a time when it was warm, wet, and alive with geological energy. A promising beginning. Mars formed from the same swirl of rock and dust that created Earth, Venus, and Mercury. But its growth was interrupted. Where Earth grew large enough to retain heat for billions of years, Mars stopped halfway smaller, lighter, and more fragile. Yet, in its youth, Mars flourished. Volcanoes erupted across its surface, pouring lava into plains and building mountains that pierced the sky. Its thin crust cooled quickly, allowing enormous volcanoes to form without collapsing. Among them arose the largest volcano in the solar system, Olympus Mons, 3 times the height of Everest, and wider than the entire country of France. To the south, massive highlands formed ancient, battered landscapes that hold the oldest Martian memories. But it was water that defined early Mars most profoundly. The rivers that once ran. Billions of years ago, Mars had a thicker atmosphere, likely dominated by carbon dioxide and water vapor. This atmosphere trapped enough heat to allow liquid water to exist on the surface. The evidence is written across the planet. Winding river channels that cut through crater walls. Ancient deltas shaped by flowing water. Shorelines that outline what once were vast northern oceans. Minerals that could only form in long-standing lakes. Mars was not merely wet, it was hydrologically active. Rain may have fallen. Rivers carved valleys. Water pooled in basins, forming lakes hundreds of kilometers wide. The northern hemisphere, lower and smoother than the south, may have held an ocean as large as the Arctic Ocean on Earth. Mars was a planet with climate, weather, and seasons. Its surface breathed with cycles of warmth and cold, wind and rain, day and night, a world of fire and ice. Even in this early chapter, Mars was a place of contrasts. Its volcanoes erupted with incredible force. Its canyons yawned wider and deeper than anything on Earth. The greatest of them, Valles Marineris, stretches more than 4,000 kilometers across the equator, long enough to span the entire United States. But alongside fire came ice. Mars's distance from the Sun meant it was always a few degrees too cold, a few grams of atmosphere too thin to maintain stability. Water froze at the poles. Glaciers crept along valleys. Snow fell across highlands. Mars balanced delicately between warmth and freezing, between oceans and ice sheets. The fading of the magnetic shield. Every planet needs protection from the Sun's harsh solar wind. Earth has its magnetic field, generated by a rotating, molten core. Mars once had one too, but its smaller size allowed its interior to cool much faster. When Mars's core slowed, its magnetic shield collapsed. This was the moment everything began to change. Without protection, the solar wind stripped away the atmosphere, molecule by molecule. The dense blanket of air that once warmed the surface thinned into a whisper. With each passing million years, Mars grew colder. Rivers shrank. Oceans evaporated or froze. Lakes dried into salty basins. Clouds dissipated. The world that once flowed with water slowly desiccated under a sky, growing clearer, thinner, and colder. The retreat of water. As the atmosphere escaped into space, Mars's water followed. Some was lost to space, broken apart by radiation. Some seeped underground, becoming ice in shadowed soils. Much of it retreated to the poles, entombed as vast ice caps layered with dust. What remained on the surface froze solid. Water became memory, written into rocks and minerals. Salt deposits marked the edges of vanished lakes. Clay minerals preserved the chemistry of ancient seas. Patterns in the ground showed where glaciers once dragged their icy weight. Mars, once blue and warm in places, became the red world, the changing sky. Mars' atmosphere transformed from thick to thin, from warm to frigid. Today, the sky is tinted pink with dust. Winds lift fine particles into global dust storms. The air is less than 1% the density of Earth's. Temperatures swing wildly between day and night. Clouds of CO2 ice drift across its pale heavens. But these changes were not sudden. They happened over hundreds of millions of years, slowly enough for the planet to remember each stage. The silent volcanoes. Olympus Mons and its volcanic siblings fell quiet long ago. The heat beneath the surface diminished. Lava tubes emptied. Mountains froze in place. But volcanic heat may still linger deep below, faint but not gone. Some regions show signs of geologically recent activity, hinting that Mars is not entirely dead inside. Its core cools slowly. Its memory fades even more slowly. A planet halfway to greatness. Mars holds a special tragedy. It was almost a second Earth. Had it been just a little larger, it could have retained heat. It could have preserved its magnetic field. It could have held its atmosphere and its oceans. Life might have taken root and flourished. Instead, Mars became a world caught between success and failure, large enough to form rivers and volcanoes, small enough to lose them, where water still hides. Though the surface is dry, water remains. Ice caps thicker than the Himalayan mountains, subsurface glaciers beneath dusty plains, underground brines that may occasionally seep to the surface, potential deep aquifers, warmed by faint internal heat. Mars is not truly dry. It is a world where water sleeps, the memory in the rocks. Mars preserves what Earth has long erased, ancient craters left untouched by erosion, river valleys billions of years old, shorelines faint but measurable, sediments layered like the pages of a book, minerals that formed in warm, neutral water. Mars remembers everything. It carries a history Earth lost to time, weather, oceans, and continents. The dream of Mars. To look at Mars today is to see a world of silence, of dust, of long shadows. But beneath its surface lies the memory of a planet that once flourished, a world where water ran freely, a world where the climate balanced gently, a world that might have felt familiar if you could visit it long ago. Mars lost its oceans, but not the memory of them, and that makes it one of the most haunting, beautiful worlds in the solar system. Long before the solar system found balance, when rocky planets were still molten, and the asteroid belt was a battlefield of shattered worlds, there was a quiet transformation taking place in the cold, outer reaches of the Sun's domain. Here, far from the heat that shaped Mercury and Venus, and far from the storms that sculpted Mars, two giants were forming, colossal planets whose gravity would determine the orbits, destinies, and survival of nearly every world around them. This is the story of Jupiter and Saturn, the first monarchs of the solar system, and how their birth reshaped everything. A cradle of ice and gas. The outer solar system was nothing like the inner one. Here, sunlight was faint, and temperatures low enough for volatile molecules, water, methane, ammonia, to condense into ice. These ices coated dust grains and allowed them to grow quickly. While the inner planets struggled through violent collisions, the outer region offered a calmer nursery. Here, Planetesimals formed rapidly, large, icy bodies, capable of gathering mass much more efficiently than their rocky cousins closer to the Sunday. They were the seeds of something immense, the birth of Jupiter, the first giant. Jupiter was the first to grow. In the cold outer disk, a massive core formed a mountain of rock and ice, at least 10 times the mass of Earth. Once it reached a critical size, its gravity became irresistible. It began pulling in the surrounding hydrogen and helium, the lightest elements, abundant in the early nebula. This was the beginning of runaway growth. Jupiter expanded rapidly, drawing in gas at a rate unmatched by any other developing world. Its atmosphere thickened, its magnetic field intensified. It became a globe of swirling storms and deepening gravity. When Jupiter reached its final size, more than 300 times the mass of Earth, it had become not merely a planet, but a force of cosmic architecture. Its birth was so powerful that it likely carved a gap in the gas disk itself. The solar system had its first ruler, Jupiter the sculptor. Jupiter's gravity extended across vast distances. It tugged on everything: planetary embryos, loose planetesimals, comets, dust, even the young Saturn. This gravitational influence reshaped the entire layout of the system. It prevented a planet from forming in the asteroid belt. It altered Mars's fate, limiting its growth. It shepherded icy bodies toward the outer disk. It scattered comets into long, elliptical orbits that still exist today. Without Jupiter, the solar system would not resemble the structure we see now. Jupiter did not merely form, it sculpted. The birth of Saturn, the second giant. While Jupiter was gathering its atmosphere, Saturn's core was forming farther out in the disk. Saturn grew more slowly than Jupiter, but it followed the same path. First, a rocky icy core, then a thick envelope of hydrogen and helium, then runaway growth powered by gravity. Although Saturn became only 1/3 the mass of Jupiter, its beauty would one day eclipse all other planets. But at this time, Saturn was young, hot, and expanding, another giant rising in the cold. Like Jupiter, it carved its own path through the disk, shaping the gas and dust around it. Together, the two giants began a gravitational dance that would define the solar system's future. The Great Migration. In the early solar system, gas giants did not stay where they formed. They moved. As Jupiter interacted with the gas disk, it drifted inward. Saturn followed, drawn by the same currents. For a time, both giants were migrating toward the Sun, a terrifying possibility, one that could have destabilized the entire planetary family. But then something remarkable happened. Saturn caught up with Jupiter. Their gravitational interaction locked them into a resonance, a synchronized orbit that reversed their migration and pushed them outward again. This two-giant partnership saved the inner planets. If Jupiter had continued inward, Earth might never have existed. This moment when Saturn caught Jupiter was one of the most important events in the history of the solar system, the birth of the moons. While the giants grew, their own miniature solar systems formed around them. Jupiter's moons took shape first. Io, heated by tidal forces, became a world of endless volcanoes. Europa grew smooth and icy, hiding a deep ocean beneath its shell. Ganymede became the largest moon in the solar system, even larger than Mercury. Callisto preserved an ancient, cratered face, a fossil of early impacts. Saturn's moons emerged as jewels in a cosmic crown. Titan, with its thick orange atmosphere and methane lakes. Enceladus, brilliant and icy, with geysers that pierced space. Rhea, Dione, Tethys, each frozen worlds of quiet beauty. Even Saturn's rings, although younger, began as icy debris orbiting the young giant. These moons preserved the memory of their giant's birth, each holding clues to chemistry, water, and the potential for life. The stabilizers of the solar system. Once Jupiter and Saturn settled into stable orbits, their combined gravity acted like an anchor. They performed several crucial roles: kept the asteroid belt from collapsing into a planet, protected Earth by deflecting comets, stabilized Mars's orbit, slowed the inward migration of icy bodies, shaped the Kuiper Belt beyond Neptune. Their presence brought order to chaos. The solar system became a structured system, with clear zones, predictable orbits, and pathways for planets to grow peacefully. Without the giant planets, the inner worlds would have been bombarded endlessly, torn from their paths, or prevented from forming altogether. Jupiter and Saturn did not simply exist. They organized. The memory of the giants. The giant planets carry within them the earliest, least altered material from the Sun's birth cloud. Their atmospheres still hold fingerprints of the primordial nebula, hydrogen from the dawn of the universe, helium untouched since the star's formation, traces of methane, ammonia, and water ice from the cold dark beyond the frost line. To study Jupiter and Saturn is to study the solar system's origin. They are living archives of creation, the legacy of their rise. By the time Jupiter and Saturn completed their migration dance and settled into their modern orbits, the solar system had transformed from chaos into symmetry. The inner worlds cooled and formed oceans. The asteroid belt stabilized. The outer worlds began to take shape. The Sun entered a long, steady adulthood. The conditions for life quietly emerged on Earth, all because the giants found their place. Their rise was not just a chapter. It was the foundation of the solar system's structure. Before Earth knew life, before Mars lost its rivers, before the asteroid belt settled into quietness, Jupiter was already awake, a colossal guardian in the outer darkness, stirring storms that would rage for billions of years. Jupiter is not merely a planet. It is the solar system's shield, anchor, and memory keeper. Its gravity has shaped destinies. Its storms have never died. Its presence has protected worlds that could otherwise have been destroyed. This is the story of Jupiter, the ancient protector, the disruptor, the giant whose influence reaches farther than any other world. A colossus born from the nebula. Jupiter formed early, within a few million years of the solar system's birth. Its core grew quickly in the icy outer disk, gathering rock and frozen volatiles until it reached a mass capable of pulling in vast clouds of hydrogen and helium. But Jupiter did more than grow. It stabilized the disk, carving paths through gas and dust, creating order from chaos. Its formation marked the moment the solar system gained a center of gravity beyond the Sun itself. Even as a newborn world, Jupiter was enormous, large enough that it could have become a star if it had been just a bit more massive. Instead, it became a failed star, a giant planet, shimmering with latent heat. The gravity that shapes worlds. Jupiter's gravity is the most powerful force in the solar system, aside from the Sunday. It influences everything around it: comets, asteroids, the inner planets, Saturn, the Kuiper Belt, even interstellar objects passing through the system. Because of this gravity, Jupiter is often called our planet's cosmic guardian. It has redirected countless asteroids that would have otherwise struck Earth. It has captured rogue comets, locked them into safe orbits, or flung them into deep space. Every world closer to the Sun has survived partly because Jupiter stood watch, a shield forged in violence. Jupiter's protective nature is not gentle. It is violent by necessity. When comets or asteroids wander too close, Jupiter shatters them, absorbs them, or slingshots them away at incredible speeds. In 1994, the world saw this phenomenon firsthand, when comet Shoemaker-Levy 9 broke apart and slammed into Jupiter, leaving dark scars larger than Earth. Jupiter took the blow, so the inner planets didn't have to. This act was not unusual. It was a tiny glimpse of what Jupiter has done for billions of years. The world of endless storms. Jupiter's atmosphere is a canvas of swirling chaos. Bands of white, tan, orange, and red wrap around the planet. Storms spiral endlessly. Wind speeds exceed 600 kilometers per hour. And then there is the Great Red Spot, a storm larger than Earth. A hurricane that has raged for at least 350 years, possibly far longer. Its winds tear through the atmosphere in loops of crimson and rust. Its size and persistence defy understanding. Jupiter does not calm. It never rests. Its storms are the outward expression of a world whose interior radiates more heat than it receives from the Sunday. Even in deep darkness, Jupiter glows. The hidden heart. Beneath the clouds lies a world no human will ever walk on. Pressure increases so rapidly that hydrogen itself transforms, first into liquid, then into metallic fluid, an ocean of metal swirling around the core. This metallic hydrogen generates Jupiter's intense magnetic field, the strongest of any planet. It creates radiation belts so powerful they can destroy spacecraft electronics. Jupiter's magnetosphere is vast. If it were visible, it would appear larger than the full moon in Earth's sky. The planet's interior is a place of crushing force, alien beauty, and superheated storms. A world without a surface, only layers of roiling, churning gas. The moons, a solar system within a solar system. Jupiter's gravitational dominance allowed it to gather dozens of moons, nearly 80 confirmed today. Its largest moons form a miniature planetary system, Io, the most volcanic world in existence. Europa, hiding a global ocean beneath its ice. Ganymede, larger than Mercury, with its own magnetic field. Callisto, ancient and heavily cratered, preserving the solar system's early scars. These moons are worlds of their own, each with unique histories and secrets. Europa, especially, may hold life beneath its frozen crust, a hidden ocean warmed by tidal flexing from Jupiter's immense gravity. Jupiter, in shaping its moons, has created environments that echo Earth's deep oceans, the migration that reshaped everything. Early in the solar system's history, Jupiter moved inward, drifting toward the Sunday. This migration could have destroyed the inner planets, but Saturn intervened, locking Jupiter into a resonance that reversed its path. Together, the two giants migrated outward again, stabilizing the entire system. This migration limited Mars's growth, prevented a planet in the asteroid belt, sculpted Earth's orbit, shaped the timing of bombardments, set the stage for life on Earth. Jupiter's journey was one of danger and balance, destruction and creation. The giant's quiet influence on Earth. Jupiter's presence changed Earth in ways subtle and profound. It protected Earth from catastrophic impacts. It sent water-rich comets inward, helping seed Earth's oceans. It stabilized long-term gravitational patterns. It slowed gravitational chaos that could have destabilized Earth's climate. Without Jupiter, Earth might have been a dry world, or an impact-scarred wasteland, or it might not exist at all. Jupiter is the reason Earth had time. Time for oceans to form, time for life to begin, time for humans to look up and wonder. The memory of the giant. Jupiter carries memories older than Earth itself. Its atmosphere preserves the chemistry of the primordial nebula. Its storms echo the early chaos of the solar system. Its moons hold pieces of planetary evolution. Its gravity writes the structure of orbits across billions of years. Jupiter remembers the beginning, and it continues to write the solar system's story through every asteroid it redirects, every comet it shepherds, every gravitational resonance it maintains. A guardian that never sleeps. As long as Jupiter orbits the Sun, it will watch over the inner planets. It will intercept the debris of cosmic time. It will send icy messengers across space. It will stabilize orbits and rhythms. Jupiter is more than mass and gas. It is a force of nature, a protector woven into the architecture of the solar system, a giant that never rests, a storm that never sleeps, a guardian whose memory spans the age of worlds. Before Saturn became the most elegant world in the solar system, crowned with luminous rings that circle it like a frozen halo, it was a quiet giant forming far from the sun, a world of calm hydrogen clouds, deep metallic storms, and soft golden light. But Saturn's beauty is not mere decoration. Its rings are a story of memory and loss, a monument created from destruction, a reminder that even broken things can become the most beautiful. This is the story of Saturn, the graceful giant whose rings hold the echoes of a shattered past. A giant born in silence. Saturn formed after Jupiter, but followed a similar path. A core of rock and ice gathered mass until it became large enough to pull in vast clouds of hydrogen and helium. But Saturn grew in a quieter region of the disk, where density was lower and sunlight weaker. It became a gas giant like Jupiter, yet lighter, more delicate, and less turbulent. Where Jupiter is intensity, Saturn is elegance. Its clouds flow in smooth bands of cream, gold, and amber. Its storms are softer, its winds faster, its atmosphere more refined. Saturn is the artist of the outer solar system, a world shaped by symmetry and subtlety. The rings that should not exist. Saturn's rings are so bright, so thin, and so perfectly arranged that they seem impossible. No other major planet has rings so vivid. The rings are made of ice, dust, fragments of rock, crystals of frozen water. Although they stretch more than 280,000 kilometers across, they are astonishingly thin, often no more than 10 meters thick, like a sheet of frost orbiting a giant. But the most haunting truth is this: Saturn's rings are temporary. They did not exist at the beginning, and they will not exist at the end. They are a fleeting memory, a beautiful accident in an ancient world. The moon that died. The rings were born from tragedy. The leading theory suggests that Saturn once had an additional moon, a medium-sized world made of ice and rock, orbiting too close to the giant. Tidal forces pulled on it relentlessly. Its orbit decayed. It moved inward, closer with each passing millennium. Finally, the moon reached the Roche limit, the point at which Saturn's gravity exceeded the moon's own ability to hold itself together. The moon shattered. Its icy mantle tore apart first, ripped into countless fragments that spread around Saturn like a bright storm. Its rocky core broke into chunks that either fell into Saturn or drifted away into space. From this devastation, the rings were born. Every sparkling arc, every bright band, every shining thread of ice is a piece of a world that no longer exists. The rings are the ghost of a lost moon. Why the rings are so bright? Most ring systems grow dark with time as dust accumulates. But Saturn's rings are dazzling. They shine because they are young, perhaps only 100 million years old. To the solar system, they are newborn. To the universe, they are an instant. Their brightness comes from water ice that has not yet weathered into darkness. Their clarity suggests recent formation. One day, millions of years from now, the rings will fade. Pieces will fall into Saturn. Others will drift outward. The elegant structure will dissolve. Saturn's beauty is temporary, and that makes it all the more poignant. The dance of shepherd moons. Small moons orbit within and around the rings, sculpting their structure like silent artists. These shepherd moons include Pan, shaped like a flying saucer, clearing a gap in the rings; Daphnis, creating ripples like waves on a frozen sea; Atlas, coated with ring particles that cling to its equator. They keep the rings sharp, defined, and symmetric. Their gravity pulls on ring particles, forming edges, waves, braids, and divisions. Without these tiny moons, the rings would be a shapeless cloud. Saturn's grace is maintained by partners as small as mountains, the moons that survive. Beyond the rings lies a kingdom of worlds. Saturn's moons, each holding its own story. Titan, the largest, is a world with a thick nitrogen atmosphere, lakes of methane, clouds of hydrocarbons, rain that falls like cold gasoline, dunes sculpted by alien winds. Titan is not merely a moon, it is a world that mirrors early Earth, except colder and stranger. Enceladus is the opposite, a small icy moon that hides a global ocean beneath its crust. Its geysers shoot water into space, forming one of Saturn's rings. These plumes contain organic molecules, salts, and chemicals associated with hydrothermal vents. Enceladus may harbor life, not hypothetical life, possible, actual, microbial life. A hidden ocean warms itself through tidal forces, like Europa does around Jupiter. Saturn, through its gravitational influence, creates environments where life could exist far from the Sunday. Saturn the sculptor, where Jupiter sculpts with force, Saturn sculpts with elegance. It shapes the orbits of icy moons, the architecture of the Kuiper Belt, the boundaries of the outer solar system, the distribution of ring particles, the resonance patterns of nearby worlds. Its gravity is less chaotic than Jupiter's, but no less influential. If Jupiter is the hammer, Saturn is the chisel. Together, they shaped the solar system, the magnetic heart. Saturn's magnetic field is mysterious, almost perfectly aligned with its rotation axis. This symmetry should be impossible under normal dynamo theory. It suggests something unknown is happening deep within Saturn's interior. Helium rain, metallic hydrogen, layered convection, a core softened by ices and rock. Whatever lies at Saturn's heart, it produces a magnetic field both refined and powerful. Saturn is not only beautiful above its clouds, it is beautiful within, a beauty built from loss. Everything about Saturn's elegance is born from impermanence. Rings from a shattered moon, plumes from a fractured Enceladus, atmospheres sculpted by migrating giants, a history tied to ice and breaking and rearranging. Saturn's beauty is not static, it is dynamic, created by events that destroyed and reshaped worlds. The rings are not symbols of stability, they are symbols of change, symbols of grief turned into grace. Saturn teaches us that loss can create beauty, that destruction can leave behind something luminous, and that the memory of a broken moon can become one of the greatest wonders of the solar system. In the distant reaches of the solar system, where sunlight arrives as a pale whisper and the warmth of the sun feels like a forgotten story, there drifts a strange and silent world, a world unlike any other planet, a world lying on its side, as though it once fell in slow motion and never stood up again. This is Uranus, the tilted giant, a planet shaped not only by the cold of the outer dark, but by an ancient tragedy, a blow so devastating it changed the planet forever. Its memory is written in the angle of its axis, the quiet of its storms, and the fragile rings that drift through its pale blue sky. A giant formed in the cold. Uranus formed in a region colder than anything the inner planets ever knew. Here, water, methane, and ammonia condensed into ices that built a large, distant world. Unlike Jupiter and Saturn with their massive hydrogen-helium envelopes, Uranus grew differently, a rocky core, surrounded by a thick mantle of water, ammonia, and methane ices, wrapped in a pale blue atmosphere of hydrogen and helium tinted with methane. This chemical blend gives Uranus its soft, tranquil color like the surface of a calm winter lake. But the serenity of its appearance hides a violent past. The collision that changed everything. In its youth, Uranus was likely upright, spinning normally like Jupiter or Earth. But early in its history, a massive impact struck the planet, a collision with an object perhaps twice the size of Earth. This world-sized blow tilted Uranus on its side by nearly 98 degrees. It didn't just rotate differently, it rolled over. The impact might have shattered its interior layers, disrupted its magnetic field, altered its rotation, created its faint ring system, formed its irregular moons. Uranus still carries the memory of this moment. It spins like a rolling ball, not a spinning top. Its poles point toward the sun at times, creating extreme seasons. A single collision rewrote the entire identity of the planet. The strange seasons of a sideways world. Because Uranus is tilted so dramatically, its seasons are the most extreme in the solar system. Each season lasts 21 Earth years. For decades at a time, one pole faces the sun in continuous daylight. The other lies in complete darkness. The equator experiences only faint glancing sunlight. When Uranus orbits half a revolution later, the roles reverse. Imagine a world where an entire hemisphere is locked in a decades-long sunset, and the other is drenched in soft twilight that never ends. Light moves in slow arcs across the horizon. Time itself feels stretched. Uranus is a planet where seasons are measured not in months, but in generations. The coldest atmosphere in the solar system. Despite being a giant, Uranus holds the record for the coldest planetary atmosphere ever measured. 224 degrees Celsius, 371 degrees Fahrenheit colder, even than Neptune, which lies farther from the Sun. Why? Because Uranus barely emits internal heat. Most giant planets release more energy than they receive from sunlight due to strong internal heating. But Uranus is quiet inside. The ancient impact may have disrupted convection, sealed heat deep within, or knocked the planet into a thermal stasis. Whatever happened, Uranus became the faintest giant, a world where winds flow silently through layers of icy gas at speeds up to 900 kilometers per hour, barely visible against its smooth, pastel surface. A sleeping giant with hidden storms, a magnetic field that should not exist. Uranus has a magnetic field, but not like Earth's or Jupiter's. It is tilted 59 degrees from the planet's rotation axis, offset far from the planet's center, lopsided, irregular, and unpredictable. This magnetic behavior has baffled scientists. Most magnetic fields form deep in a planet's core, but Uranus's seems to come from the icy mantle, from layers of water and ammonia compressed into exotic states, super-ionic water, ammonia-rich oceans, electrically conductive slush. The magnetic field wobbles as Uranus rotates, shifting like a broken compass. It is a planet whose very heartbeat was knocked off-center by ancient trauma, the rings of ice and shadow. Uranus has rings, darker and narrower than Saturn's, thin as shadow lines, composed of icy particles coated with radiation-darkened dust. These rings likely formed from shattered moons, debris from ancient impacts, leftover fragments of the collision that tilted the planet. The rings are faint, but they trace the ghost of Uranus's violent past, the moon's children of a broken world. Uranus is surrounded by 27 moons, many named after characters from Shakespeare and Alexander Pope. The major five, Titania, Oberon, Umbriel, Ariel, Miranda, each reveal different stories. Ariel, the most geologically active, scarred by canyons and smooth plains. Miranda, a bizarre world stitched together from shattered pieces as if rebuilt after destruction. Titania and Oberon, large icy moons with hints of subsurface oceans. Umbriel, ancient and dark, a moon that remembers the deepest past. These moons may have been reformed after Uranus's great impact, or they may have survived and simply been forced into new orbits. Around Uranus, everything carries the memory of upheaval, a planet that rolls through space. As Uranus orbits the Sun, its tilted axis causes it to move like a rolling marble. Its equator is nearly perpendicular to its path. Its poles sweep through sunlight and darkness like lanterns rotating in slow motion. From a distance, Uranus appears serene. Up close, serenity hides trauma, a world shaped by a single, catastrophic event. It rolls in silent dignity, holding the memory of impact with every spin. What Uranus teaches us. Uranus is a lesson in cosmic fragility. It shows that one collision can change a planet forever. Stability is rare in a young solar system. Even giants can fall. Beauty can be quiet, pale, and understated. Memory can be written not in color or storms, but in tilt and motion. Uranus is not bright like Jupiter, nor dramatic like Saturn, nor wild like Neptune. It is gentle, ghostly, and strange. A giant that whispers, not roars. The pale giant in the dark. At the edge of the solar system's visible realm, Uranus drifts in cold silence. It receives sunlight too faint to warm it, yet enough to cast a soft glow across its cloud tops. It rotates in a toppled posture, forever remembering the blow that shaped its fate. It is a planet defined not by power, but by the memory of collapse and the quiet beauty that followed. Uranus is the poetry of the outer solar system, a world of pale light, slow seasons, tilted destiny, and ancient sorrow. In the farthest reaches of the solar system, where sunlight fades into a pale echo and darkness becomes almost complete, there lies a planet of impossible storms, a world so distant that a single year lasts 165 Earth years, a world colder than nearly any other, yet home to the fastest winds ever recorded in the entire solar system. This is Neptune, the distant giant whose storms whisper the memory of the outer dark. Neptune is the last true planet, the final sentinel before the Kuiper Belt, a world shaped not by warmth or collisions, but by cold, distance, and silence. Yet Neptune is anything but quiet, the last giant born. While Jupiter and Saturn formed early in the swirling disk of gas, and Uranus took shape after a devastating impact, Neptune formed even farther out, colder, darker, slower. Ice collected into a massive core, gathering methane, ammonia, and water ices into a mantle around it. Hydrogen and helium formed a thin atmosphere. Methane in particular absorbed red light, scattering blue, giving Neptune its deep, powerful color. But Neptune's birth was not peaceful. It may have formed closer to the Sun and then been pushed outward by interactions with Jupiter and Saturn. This migration shaped the Kuiper Belt, altered Pluto's orbit, and organized the outer solar system. Wherever Neptune formed, it ended up as the most remote planet, a giant pushed to the edge of the Sun's domain, a world of unexpected energy. At Neptune's distance, sunlight is incredibly weak, just 1/900th of what reaches Earth. By all logic, Neptune should be quiet, dark, frozen, still, and yet, Neptune radiates more than twice the heat it receives. Its storms are fiercer than the storms on Jupiter. Its winds reach 2,100 kilometers per hour, 1,300 miles per hour, faster than the speed of sound on Earth. Where does this power come from? Perhaps leftover heat from its formation, gravitational compression, sinking methane droplets releasing energy, interior convection stirring like a deep ocean. Whatever the cause, Neptune refuses to rest. It is a world where darkness fuels motion, the great dark spot. When Voyager 2 flew past Neptune in 1989, the only spacecraft ever to visit, it found a colossal storm in the southern hemisphere. The Great Dark Spot, a swirling vortex the size of Earth. It was cold, violent, fast, mesmerizing. But unlike Jupiter's Great Red Spot, which has lasted for centuries, Neptune's storms appear and disappear over years, shifting with the winds. The Great Dark Spot observed by Voyager vanished by the time the Hubble telescope looked again. Yet new dark spots appear regularly, tempestuous memories swirling in Neptune's upper atmosphere. The deep blue mystery. Neptune's color is deeper than Uranus's pale teal, despite similar atmospheric composition. This suggests different cloud structures, more dynamic mixing, varying methane concentration, unique aerosols absorbing light. Neptune's blue is a color of depth, a blue that seems almost to glow from within, a blue born of cold storms and hidden heat. The tilted magnetic heart. Like Uranus, Neptune's magnetic field is strange, tilted 47 degrees off-axis, offset far from the planet's center, lopsided and asymmetrical. This strongly hints that Neptune, too, generates its field in the icy mantle, not at the core. These magnetic quirks create auroras, but not like Earth's polar lights. Neptune's auroras dance unpredictably, flickering across unexpected regions. Even light behaves differently at this distance. The captured world. Neptune's largest moon, Triton, is unlike any other major moon. It orbits backwards, retrograde, meaning it did not form around Neptune. Neptune captured it, likely pulling it from the Kuiper Belt. This capture event was catastrophic. The gravitational chaos may have shattered Neptune's original moon system. Today, Triton is covered in nitrogen ice, spewing geysers of dark material, geologically active, younger looking than expected, likely hiding a subsurface ocean, eerily similar to Pluto. Triton is a world that remembers where it came from, a refugee from the icy edge of the solar system, now held in Neptune's gravity. Millions of years from now, Triton will spiral inward and break apart, forming new rings around Neptune. The story of Saturn may replay itself in the far future. The moons and the rings. Neptune has a small collection of moons beyond Triton: Nereid, Proteus, Larissa, Despina, and others, each scarred, irregular, and ancient. Its rings are faint, composed of dark dust and ice. They are not uniform. Some contain dense arcs that defy the normal spreading expected of ring particles. These arcs are kept intact by the gravity of small shepherd moons, a delicate balance in the outer dark. Neptune's rings are not beautiful like Saturn's. They are subtle, ghost-like, and fractured. They are memories of past collisions, barely visible against the void. The winds of the edge. Neptune's winds are its most defining feature. How can a world so cold, with so little sunlight, generate such powerful storms? Perhaps because friction is low. Atmospheric density is ideal for acceleration. Heat rises from deep inside the planet. The rotation is fast, a 16-hour day. Whatever the reason, the winds on Neptune howl through endless night, carrying storms the size of continents across belts of frozen gas. These winds are the solar system's final breath, the last great movements before the silence of interstellar space. They are the voice of a world shaped by distance, a world that remembers the dark, the planet of the edge. Neptune is the boundary between the solar system we know and the ancient icy frontier beyond. Its gravity sculpts the Kuiper Belt, stabilizes Pluto's orbit, sets the outer resonance patterns, protects the inner worlds from drifting icy bodies. It is a guardian at the edge, pulling on everything near the darkness. In many ways, Neptune is the solar system's horizon, the transition between sunlight and the great unknown, a memory written in ice and wind. Neptune's story is not one of violence like Mars, or tragedy like Uranus, or creation like Jupiter. Its story is of endurance, a world that thrives in cold, shines in faint light, and moves with unbelievable energy. Despite being so far from the Sunday, it remembers a time when the solar system was crowded and chaotic. It survived migrations, collisions, changes in structure, and now it drifts quietly, its deep winds echoing through the far reaches of space. Neptune is the final note of the solar system's great symphony, a low, distant, blue chord that never stops vibrating. Far beyond Neptune, where sunlight fades into a cold whisper and space grows quiet enough to hear the memory of creation itself, lies a vast and ancient frontier, a realm of ice, of shadows, of worlds that never changed, a place where time slows and history sleeps. This is the Kuiper Belt, a frozen archive holding the oldest, most untouched material from the birth of the solar system. If the inner planets are the solar system's children, and the gas giants its guardians, then the Kuiper Belt is its memory, a ring of frozen worlds. The Kuiper Belt stretches from about 30 AU to more than 50 AU from the Sun, a region so large that Earth could orbit inside it for centuries without reaching the end. Unlike the asteroid belt, which is rocky and violent, the Kuiper Belt is icy and quiet. It contains frozen worlds, dwarf planets, comet nuclei, objects of rock and ammonia, methane glaciers, nitrogen frost, ancient ices untouched for billions of years. Each object is a time capsule, preserved by cold so extreme that chemistry itself slows to a crawl. At temperatures near 220 degrees Celsius, 364 degrees Fahrenheit, nothing melts, nothing flows. Everything remains exactly as it was since the solar system was young. The forgotten outer disk. When the solar system formed, the protoplanetary disk extended far beyond Neptune. The inner region gave birth to rocky planets. The mid-region formed the gas giants. But the outer region, cold, thin, and slow, produced small icy bodies that grew too slowly to become planets. These bodies were the building blocks of worlds that never were. Some were pushed outward, some were scattered, some remained in stable orbits. Together, they formed a vast reservoir, the Kuiper Belt. This region is not debris, it is survival. These objects avoided collisions, avoided migration, avoided destruction. They are almost exactly as they were 4.5 billion years ago. No tectonics, no erosion, no resurfacing, just silent preservation. The sculptor, Neptune. The Kuiper Belt would not exist without Neptune. As Neptune migrated outward early in solar system history, it plowed through the outer disk. Its gravity pushed some bodies away, pulled others inward, and trapped many into orbital resonances. These resonances, mathematical harmonies between Neptune and Kuiper Belt objects, created distinct families: the Plutinos, the Twartinos, the classical belt objects, the scattered disk objects. Pluto itself is a Plutino, locked into a stable gravitational rhythm with Neptune. Every object in the Kuiper Belt dances to Neptune's distant, invisible gravity. The Plutinos' resonance survivors. Objects in the 3-2 resonance with Neptune complete 2 orbits around the Sun for every 3 orbits Neptune makes. This resonance protects them. It keeps them from drifting into dangerous paths. It ensures they never collide with Neptune, even though they cross its orbital distance. Pluto is the most famous of them, but thousands more exist. Dark, icy, mysterious. Plutinos are like distant cousins living in rhythm with a giant they never meet. Classical Kuiper Belt objects. The cold and the hot. The classical belt contains 2 populations: cold classicals, with pristine, circular orbits, untouched since the solar system's birth. Hot classicals, with more inclined and eccentric orbits, stirred by Neptune during migration. Cold classicals are the purest fossils in the solar system. Their colors are bright red, rich in complex organic molecules. Their surfaces have never melted or shifted. They are the memory core of the Kuiper Belt. The scattered disk, the wild ones. Some objects were hurled outward by Neptune's gravity into unstable, elongated orbits. These are the scattered objects, and they wander far into deep space, toward the inner solar system, into paths that may eventually become cometary trajectories. The scattered disk is chaotic, violent, and active even at the edge of the Sun's influence. The famous dwarf planet Eris belongs here, larger than Pluto and responsible for redefining planet. Dwarf planets of the Kuiper Belt. The Kuiper Belt is home to several known dwarf planets, each a frozen world with its own history. Pluto, the most iconic, with nitrogen glaciers, methane ice, towering mountains, a thin, shifting atmosphere, a heart-shaped basin of frozen nitrogen. Pluto is complex, alive with slow glacial movement, active even at 230 degrees Celsius. Eris, massive, reflective, and colder than Pluto. Its discovery reshaped astronomy and led to the reclassification of planets. Haumea, fast-spinning, elongated like an egg, has a ring rare for a dwarf planet. Makemake, covered in methane frost, glowing in faint reddish hues. Quaoar, large enough to hold a thin methane atmosphere at times. Each is a survivor of an age long vanished. The birthplace of comets. Many comets originate in the Kuiper Belt. These include short-period comets, icy visitors like Halley, objects nudged inward by Neptune's gravity. When a Kuiper Belt object falls toward the Sun, its ice sublimates, creating tails of gas and dust. Comets are messengers from this frozen frontier, carrying ancient ices into the warm regions near Earth, delivering water, organic molecules, and chemical seeds that may have helped life begin. The Kuiper Belt is not merely a relic, it is a giver, the edge of the known solar system. Beyond the Kuiper Belt lies the scattered disk, and farther still, the mysterious Oort cloud, a spherical shell of icy bodies that extends halfway to the next star. The Kuiper Belt is the inner gateway to this deep cosmic wilderness. It marks the transition from the structured solar system, with planets and resonances, to the vast, uncharted region where the Sun's light is weaker than starlight. It is where the solar system's memory fades into interstellar night, a memory preserved in ice. The Kuiper Belt is the most ancient region we can still study directly. Its objects hold original ices, primordial organics, unaltered minerals, the chemistry of the protosolar nebula, clues to planetary migration, the history of cometary material, the formation timeline of the early solar system. Nothing else preserves so much. Earth melted its crust, Venus burned, Mercury shrank, Mars froze then dried. Jupiter and Saturn swallowed everything. Uranus toppled, Neptune howled, but the Kuiper Belt remained, unchanged, unmoved, unaffected, a frozen library of everything the solar system once was, a silent frontier. If you stood on a Kuiper Belt object, the Sun would look like a bright star, not a disk, not a warming presence, just a distant point of light. Your shadow would be barely visible. Your breath would fall as ice crystals. Your footsteps would never melt into the surface. This is a region where memory sleeps, not erased, not rewritten, but preserved in eternal winter. The Kuiper Belt is the solar system's memory palace, a place where the oldest stories remain untouched, waiting for us to uncover them. In the dim outer reaches of the solar system, where daylight fades into a pale memory and shadows stretch for millions of kilometers, there drifts a small, icy world with a beating heart. A world once called a planet. A world later pushed aside, renamed, reclassified, and debated. A world that the solar system itself has not forgotten, even if humanity briefly did. This is Pluto, the outcast, the wanderer, the little world with the biggest story. Pluto remembers everything. A world born in the frozen dawn. Pluto formed in the icy outskirts of the young solar system, within the same primordial disk that created the Kuiper Belt. Unlike the rocky worlds or the giant planets, Pluto never had a chance to grow large. The region was too cold, too thin, too distant for rapid accretion, and yet Pluto formed anyway. A body of rock and nitrogen ice, wrapped in methane frost, covered with organic tholins that paint it reddish-brown, possessing a complex interior structure and potential warmth deep below. Pluto became one of the largest survivors of the ancient outer disk, a relic that the solar system kept as a reminder of its icy beginnings. A strange, tilted orbit. Pluto does not follow the normal rules. Its orbit is elliptical, stretching far from the Sun and then drawing closer, tilted, 17 degrees above and below the plane where most planets travel. Resonant, locked with Neptune in a 3-to-2 gravitational rhythm. For every 3 orbits Neptune makes, Pluto completes 2. This resonance ensures they never collide. A cosmic dance choreographed billions of years ago. Pluto is both part of the solar system and outside its main structure. An outlier by design, the heart of ice. Sputnik Planitia. When NASA's New Horizons spacecraft flew past Pluto in 2015, it found something unexpected. A brilliant, smooth, icy plain shaped like a giant heart. This region, Sputnik Planitia, is made of frozen nitrogen so reflective it glows beneath dim sunlight. It is vast, active, constantly reshaped, geologically young. Cellular patterns on its surface suggest convection, nitrogen ice rising and falling like a slow-motion ocean. A heart that beats once every few million years. This icy heart rewrites what we thought small worlds could do. Pluto is not dead. It is alive with slow, frozen motion. A world with an atmosphere that comes and goes. As Pluto approaches the Sun during its long, 248-year orbit, part of its nitrogen ice sublimates into a thin atmosphere. This atmosphere is mostly nitrogen, with traces of methane and carbon monoxide, blue in color. Surprisingly layered with hazes, it forms towering, delicate sheets of atmospheric haze that rise 150 kilometers above the surface, more than 10 times the height of similar features on Earth. But as Pluto drifts away again, its atmosphere collapses, freezing back onto the ground. It breathes in ice and exhales vapor over centuries. A world with seasons longer than civilizations. Mountains of water ice. Pluto's surface temperature is near 230 degrees Celsius, so water ice behaves like stone. It forms mountains as tall as the Rockies, Hillary Montes, Tenzing Montes. These peaks rise dramatically above nitrogen plains. Their slopes are sharp and their structure is rugged, like cliffs carved in frozen granite. Water ice is the planet's bedrock. Nitrogen and methane are its snow. Canyons, glaciers, and ancient dark lands. To the west of the heart lies Cthulhu Macula, a dark, reddish region covered with thick organic materials deposited by sunlight breaking apart methane. To the east lie brilliant glaciers that flow slowly across the plains, guided by gravity the way glaciers flow on Earth. Farther south stand massive canyons, some deeper than the Grand Canyon, stretching hundreds of kilometers. Pluto's surface is not a simple, frozen wasteland. It is dynamic, varied, and textured, a world of frozen geology still unfolding. The secret beneath Pluto's crust. One of the great surprises from New Horizons is the possibility that Pluto harbors a subsurface ocean beneath its ice shell. This ocean may be salty, warm enough to remain liquid, insulated by thick layers of nitrogen and water ice. Tectonic features, cracks, ridges, and fault lines suggest internal pressure from such an ocean. If true, Pluto becomes part of a growing family of ocean worlds, alongside Europa, Enceladus, Titan, and others. Life here would be unlikely, but not impossible. Even at the edge of the sun's light, warmth can survive. The moon that would not let go. Pluto's largest moon, Charon, is half Pluto's size, so large that the two orbit a shared center of mass outside Pluto's surface. This makes Pluto-Charon a double world, not a planet and moon in the traditional sense. Charon bears massive canyons, fractured plains, evidence of ancient cryovolcanism, a northern hemisphere stained with reddish tholins escaping from Pluto. Together, the pair spin around each other in perfect synchrony. Each always shows the same face to the other, a gravitational embrace frozen in time. Why Pluto was demoted. Pluto's reclassification in 2006 was not an insult. It was a revelation. Astronomers discovered dozens of similar-sized objects in the Kuiper Belt, including Eris, Haumea, Makemake, and others. Pluto was not alone. It was the first of many. Recognizing Pluto as a dwarf planet placed it in its rightful family, the family of icy outer worlds. But Pluto never lost its magic. Among all dwarf planets, Pluto remains the most complex, the most dynamic, and the most beloved. A world too rich to be forgotten. The memory of the outcast. Pluto remembers the ancient Kuiper Belt, the original solar nebula, the time before Neptune migrated, the gravitational dance that preserved its orbit, the ice that formed before Earth existed, the slow pulse of an atmosphere that freezes and reforms. Pluto is the solar system's diary, small, quiet, distant, but overflowing with history. It is a world that challenges our expectations, teaches us humility, and reminds us that wonder often lies in the smallest places. Pluto may not be a planet, but it is one of the most interesting worlds the solar system has ever created. And its heart still beats, slow and bright, in the coldest corner of the sun's reach, in the frozen frontier of the outer solar system, where sunlight weakens into a dim glow and temperatures fall low enough to freeze air itself, lie three of the most extraordinary worlds ever discovered. They are not planets, they are moons. Yet each of them holds something Earth once thought was unique. Liquid water, vast, hidden, and alive with possibility. Titan, Europa, Enceladus, three worlds that should be dead and silent. Yet beneath their frozen crusts, something stirs. These are the ocean worlds, guardians of the solar system's deepest biological secrets. Titan the moon, with an Earth-like soul. Titan, Saturn's largest moon, is bigger than Mercury. From afar, it appears as a golden sphere wrapped in thick haze, the only moon with a substantial atmosphere. Its atmosphere is thicker than Earth's, made mostly of nitrogen, filled with methane and complex hydrocarbons, cold enough that methane forms lakes, rivers, and rain. Titan is the only place besides Earth known to have stable liquids on its surface. But these liquids are not water. They are methane and ethane hydrocarbon seas shimmering under an orange sky. A methane weather cycle. Titan has methane clouds, methane rain, methane fog, methane storms, river channels carved by methane flows, lakes and seas filling its polar regions. It is an alien version of Earth's hydrological cycle. If you stood on Titan, Raindrops of liquid methane would fall softly on your helmet, forming ripples on black, oily seas. The world would seem familiar, yet impossibly strange. The hidden ocean. Beneath Titan's icy crust lies something even more important. A global subsurface ocean, rich in water and ammonia. This ocean may be salty, warm, thick with organic compounds falling from the atmosphere. Titan has all the ingredients required for prebiotic chemistry. It may not host life as we know it, but it may host life we've never imagined. Europa, the moon that whispers of life. Europa, one of Jupiter's 4 great moons, is a world of smooth, bright ice, streaked with dark, broken lines. It looks like a cracked marble, beautiful, fragile, and enigmatic. Europa is one of the most compelling locations for life in the solar system, an ocean beneath the ice. Beneath its icy shell lies a global ocean containing more water than all of Earth's oceans combined. This ocean is kept warm by tidal heating from Jupiter's gravity, friction within Europa's rocky mantle, possible hydrothermal vents on the seafloor. Pressure under the ice may support deep oceans, underwater volcanoes, chemical gradients, energy sources for life. If Earth-like organisms exist in the solar system outside Earth, Europa is their most likely home. The cracked surface. Europa's surface is extremely young, constantly being repaved by upwelling water, reshaped by tidal stress, fractured into long, dark lineae that stretch for thousands of kilometers. These lines might be places where the ocean interacts with the surface. They may carry salts and organic material upward. Europa's ice breathes, rising, falling, breaking, freezing, a frozen skin covering a living sea, plumes of water. Telescopes and spacecraft have detected plumes of water vapor erupting from Europa's south pole. These plumes may originate from the subsurface ocean, contain salt and organic molecules, offer a way to sample Europa's ocean without drilling through kilometers of ice. Europa does not hide completely. It leaks its secrets into space. Enceladus, the icy moon that bleeds water. Enceladus, one of Saturn's smaller moons, should be an unremarkable ball of ice. Instead, it is one of the most astonishing worlds ever found. Beneath its bright, reflective surface lies an ocean warmed by tidal forces, and from cracks near its south pole called the Tiger Stripes, Enceladus sprays this ocean into space. The geysers of life. These geysers eject water vapor, ice grains, salts, silica particles, complex organic molecules, everything needed for life. A spacecraft flying through these plumes like NASA's Cassini did can taste the chemistry of an alien ocean. Inside the droplets, Cassini detected hydrogen gas, methane, organic molecules, evidence of hydrothermal activity on the seafloor. On Earth, hydrothermal vents are home to ecosystems teeming with life. If any life exists on Enceladus, it could be living around such vents. A world too active to be dead. Enceladus should have run out of heat long ago, but tidal flexing from Saturn keeps its interior warm, driving convection in its ocean, and pushing water through cracks in the ice. Every plume is a message. Something warm and dynamic lives inside me. The 3 ocean worlds and their secrets. Titan, Europa, and Enceladus each hold a different clue to life beyond Earth. Titan, organic chemistry. Titan offers complex hydrocarbons, methane weather, a warm subsurface ocean. Titan may replicate the earliest conditions on prebiotic Earth. Europa energy plus water. Europa has liquid water, tidal heating, possible hydrothermal vents, salts and organic chemistry. If life exists elsewhere, Europa is one of the strongest candidates. Enceladus, direct evidence. Enceladus provides plumes of ocean water, hydrothermal activity, complex organics, detectable chemical energy. Among all ocean worlds, Enceladus is the one humanity could sample most easily. Why these moons matter? For most of human history, Earth was the only known world with water, the only world with chemistry, the only world with oceans. Then we discovered these icy moons, and everything changed. The question is no longer, is Earth unique? It is now. Where else in the solar system might life be hiding? Titan, Europa, and Enceladus are three answers, three worlds where conditions align in ways that echo the origins of life on Earth. If life exists elsewhere in the solar system, these are the places we will find it. Long before oceans shimmered on Earth, long before the sky turned blue, long before continents cooled from molten stone, something small and icy came wandering through the darkness. A messenger, a traveler, older than mountains, older than planets, older even than the Sunday. A comet. Comets are the solar system's memory keepers, carrying untouched material from the dawn of creation. They wander vast orbits for millions of years, returning again and again to the sun like ghosts retracing ancient footsteps. And in their frozen hearts, comets carry secrets. Secrets of water, carbon, organic molecules, and the very chemistry that may have sparked the first breath of life on Earth. The birth of comets, fragments of the primordial nebula. Comets formed in the outermost regions of the solar system, where temperatures were so cold that water froze into glassy shards, carbon dioxide turned to ice, methane and ammonia crystallized, organic molecules became trapped in frozen cages. Dust from dying stars mixed with newborn ice, forming strange, porous objects, half rock, half snow, fragile yet ancient. These were the first comets, tiny frozen libraries drifting at the solar system's edge. Two great reservoirs became their home, the Kuiper Belt, birthplace of short-period comets like Halley, the Oort cloud, a spherical shell of trillions of icy bodies extending halfway to the nearest star. The Oort cloud is so vast that a comet may take millions of years to complete a single orbit. These comets are older than Earth, older than the Moon, older than everything we know. The Great Migration. When Jupiter and Saturn migrated through the young solar system, they disrupted countless icy planetesimals. Some were thrown inward, toward the Sunday. Some were thrown outward, to form the Oort cloud. This violent scattering created a cosmic diaspora. Comets became wanderers, carrying chemistry across the solar system like drifting seeds. Every world they touched was changed, especially Earth. How comets brought water to Earth. Early Earth was molten and dry. Volcanoes belched steam, but the planet lacked stable bodies of water. So where did our oceans come from? One possibility lies with comets. As icy comets rained down on Earth during the late heavy bombardment, around 4 billion years ago, they delivered vast quantities of water, complex organic molecules, carbon compounds, the building blocks of amino acids. Each impact released enormous plumes of vapor that eventually condensed into rain. Over millions of years, cometary water helped fill the basins that became Earth's first oceans. Earth did not create its water alone. The solar system delivered it. The oceans are a cosmic inheritance, the chemistry of life in cometary ice. When spacecraft like Rosetta visited Comet 67P, Churyumov-Gerasimenko, they found amino acid, glycine, phosphorus, organic molecules, carbon-rich dust, complex hydrocarbons, prebiotic compounds. This means comets carry the same molecular ingredients needed for proteins, cell membranes, nucleic acids, the earliest chemical reactions of life. The seeds of biology existed in cometary ice long before Earth cooled. Comets were cosmic delivery systems for life's ingredients. They were the universe's first chemists. The awakening of a comet. When a comet approaches the Sun, its frozen nucleus awakens. Heat turns ice into vapor. Jets of gas erupt through cracks. Dust is released in shimmering plumes. A glowing coma forms. A temporary atmosphere around the nucleus. A tail streams behind it, stretching millions of kilometers. This transformation is like a frozen heart bursting into flame. The two tails, one of dust, one of charged gas, reveal the comet's ancient interior, lifted into sunlight for the first time in eons. Each tail is a message written in ice and dust, a message billions of years old. The dance with the sun. Comets follow extreme orbits. Some return every few decades, Halley. Others visit once and never return. Some dive into the Sunday. Others are torn apart by tidal forces. Some become dormant, turning into dark, rocky bodies. Their journeys shape the solar system. They scatter organic material. They collide with planets. They feed atmospheres. They form meteor showers as fragments remain in orbit. Earth's annual meteor showers, Perseids, Leonids, Geminids, are the memory trails of ancient comets. Every shooting star is a grain of dust, burning a story into our atmosphere. Comets as bringers of possibility. It is possible, even likely, that life's earliest chemistry on Earth began with cometary material. When comet fragments mixed with warm volcanic pools or hydrothermal vents, they may have triggered the first polymers, the first membranes, the first replicating molecules, not life itself, but the proto-life chemistry that led to it. Earth did not start its story alone. It was seeded by wandering messengers from deep space. We are, in a sense, the children of comets and other worlds. Earth was not the only world comets touched. They delivered water to Mars, organics to Europa, energy-rich material to Titan, nitrogen and methane to Pluto, volatile compounds to the asteroid belt. Every icy world in the solar system carries traces of cometary chemistry. Comets are the threads that weave the solar system together, the memory of the long orbit. A comet spends almost all its life alone in the dark, cold, silent, waiting. Only for a brief moment, a few months, a few years, does it bloom near the Sunday, and then it returns to darkness. But on each journey inward, it leaves something behind: dust, ice, organics, meteor streams, water, possibilities. Comets write history, not in stone, but in the chemical footprints they scatter across the solar system, the eternal archive. In the Oort cloud, trillions of comets drift in slow orbits. They are the oldest surviving bodies in the solar system, preserved by cold and silence. Each one is a frozen page of the sun's earliest story. Each one holds clues to the chemistry that existed before planets were born. If we want to understand where we came from, we must listen to comets. They are the keepers of the beginning. Before humans understood the solar system, before we mapped Mars, before we saw Saturn's rings up close, before we knew what Pluto looked like, we dared to send machines into the unknown. Small, fragile, imperfect machines, powered by plutonium hearts and guided by golden instructions. They were the Pioneer, the Voyager twins, and decades later, New Horizons. They carried cameras, instruments, computers, and something more: the memory of humanity, etched onto metal plates, golden discs, and radio pulses. This is the story of the probes that became our first interstellar messengers, the first whispers of our species traveling into the deep night. The pioneer journeys, the first steps into the outer dark. In the early 1970 seconds, Long before smartphones or internet or digital cameras, NASA launched Pioneer 10 and Pioneer 11. Small, simple, light enough to lift on modest rockets, yet they carried courage beyond measure. Pioneer 10, 1,972, the first spacecraft to cross the asteroid belt, visit Jupiter, leave the inner solar system. Its close approach to Jupiter in 1973 revealed the planet's radiation belts, its immense magnetic field, its swirling storms, the scale of the Great Red Spot. Gravity from Jupiter flung Pioneer 10 onto an escape path from the solar system. Pioneer 11,197.3. 1 year later, Pioneer 11 followed. It visited Jupiter, then became the first probe to fly past Saturn, reveal the planet's rings from close range, measure Titan's environment. Its Saturn flyby sent it outward too into interstellar space. Both Pioneers eventually fell silent, but before they left, each carried a message. The Pioneer plaque, designed by Carl Sagan and Linda Sagan, a simple diagram, a human man and woman, the location of Earth, the map of pulsars for navigation. It was our first cosmic introduction. Hello, we are here. The probes are now drifting into eternity. Silent ambassadors of a species that dared to dream. The greatest journey in human history. In 1977, 2 new spacecraft launched, Voyager 1 and Voyager 2. They were bigger, stronger, smarter than the Pioneers, equipped for a rare gravitational alignment that occurs once every 176 years. Jupiter, Saturn, Uranus, Neptune. A planetary grand tour. Only the Voyagers could take it. Voyager 1, Jupiter and Saturn. Voyager 1 revealed Jupiter's lightning, active volcanoes on Io, first seen outside Earth, Europa's cracked, icy surface, Saturn's rings in exquisite detail, Titan's thick atmosphere. After Saturn, Voyager 1 angled upward out of the ecliptic, on a trajectory that would take it into interstellar space. Voyager 2, the only probe to visit Uranus and Neptune. Voyager 2 became humanity's ultimate explorer. It discovered 10 new moons of Uranus, Uranus's strange magnetic tilt, Neptune's great dark spot, Triton's nitrogen geysers, Neptune's supersonic winds, ring arcs, and unexpected ice giants' dynamics. Voyager 2 is the only spacecraft in all of human history to see the ice giants up close. No one else has ever returned since. The Golden Records. Each Voyager carries a golden record, a metal disc coated in gold, containing music from around the world, greetings in 55 languages, sounds of nature, diagrams of Earth, a map of pulsars, mathematical instructions, the image of our species. It is the time capsule of Earth, a message to whoever may one day find it. If intelligent life ever intercepts Voyager, they will hear our heartbeat. The crossing into interstellar space. Both Voyagers eventually reached the boundary where the Sun's influence ends. Voyager 12012 became the first human-made object ever to enter interstellar space. It now travels through the plasma between the stars, a place no human will see for thousands of generations. Voyager 22018 crossed the boundary 6 years later and continues outward through the starless dark. Their plutonium power slowly fades. Their instruments fall silent one by one, but their journey continues for millions of years. They will orbit the galaxy long after Earth is gone. New Horizons, the long road to Pluto. Launched in 2006, New Horizons was humanity's fastest spacecraft. It flew past Jupiter for a gravity assist, then traveled 9 years toward a world we had never seen clearly, Pluto. On the 14th of July 2015, for a few breathtaking hours, New Horizons became the first probe to visit Pluto. It captured Sputnik Planetia's heart-shaped glacier, nitrogen mountains, methane ice plains, haze layers in Pluto's atmosphere, the dark red stretches of Cthulhu Macula, Charon's massive canyons and fractured crust. Before New Horizons, Pluto was a blurry pixel. After New Horizons, it became a world. But New Horizons' journey didn't end there. In 2019, it visited Arrokoth, a Kuiper Belt object, 6.6 billion kilometers away, a pristine relic from the solar system's formation. Today, it continues deeper into the Kuiper Belt, studying particles, dust, and distant icy worlds. Why these missions matter? These spacecraft are not just machines. They are extensions of human curiosity. They are the eyes of Earth, sent into places we cannot go. They taught us that Jupiter's moons are alive, that Saturn's rings are young, that Uranus fell sideways, that Neptune howls in the dark, that comets hold ancient chemistry, that Pluto is complex and beautiful, that Earth is a blue dot suspended in the universe. Carl Sagan once said, "The voyages are the ships of our imaginations," and he was right. The memory we sent into the stars. The Voyagers, Pioneers, and New Horizons carry something unique, the memory of humanity. In the vacuum of space, nothing decays, nothing rusts, nothing erases. These probes will outlast civilizations, nations, languages, continents, species, Earth itself. Long after the sun swells into a red giant, long after the planets disperse, Voyager will still be traveling. If someday, far in the future, another intelligent species discovers one of our probes, they will learn that we once lived, that we once listened to the ocean waves, that we once laughed, sang, dreamed, that we reached for the stars before we understood them. These probes are not our tools. They are our legacy, humanity's first footsteps into the dark. In the quiet expanse between the planets, in the stillness where sunlight thins into silver dust, the solar system holds its breath. It has existed for 4.6 billion years, long before oceans formed on Earth, long before Saturn's rings shimmered into being, long before comets carved their icy paths through the dark. And now, at last, there is something new within it. Us, humanity, the only creatures, so far, to awaken under its light and wonder where we came from. For billions of years, the solar system had no eyes, no ears, no memory except in stone and ice. Then Earth grew life. Life grew minds. Minds grew questions. And through those questions, the solar system began to see itself, reflected in our curiosity. This final chapter is not about planets or moons. It is about what the solar system remembers when it looks at us. The Earth, the first world to know itself. Earth has watched life rise, fall, transform, and begin again. It nurtured oceans where chemistry awakened. It shaped continents that drifted like slow, dreaming giants. It allowed forests to inhale sunlight and breathe out oxygen. It gave mammals a chance after extinction. It gave humans a place to stand and wonder. Earth remembers the footsteps of every creature that has ever touched its soil. But humanity did something unprecedented. We looked back. We studied the sky. We mapped the moon. We charted the planets. We launched machines into the dark. Earth, for the first time, became a world that knew its place in the cosmos. The moon, our quiet witness. For billions of years, the moon drifted in silence. Then humans arrived. Not by accident, not by chance, but by intention. We left footprints on its surface, footprints that will remain for millions of years, longer than any city on Earth, longer than any mountain. The moon remembers. The first human bootprint, the first words spoken on another world. The flag left not as a claim, but as a message. The moment when a species born of oceans walked on dust older than time. The moon will keep these memories long after Earth erases ours. Mars, the world that watches us in return. Mars once had rivers. Now we send rovers. They crawl over ancient channels, taste the dust, listen to the wind, and wait for commands from a small blue dot in the sky. Mars remembers water. We remember that Mars once resembled Earth. Between our two worlds lies a connection, a shared story of potential. Perhaps one day, footprints will join the rover tracks. Perhaps Mars will remember the moment humanity became a multi-planet species. Venus and Mercury, the lessons of what could have been. Venus shows us the power of imbalance, a world that lost its oceans to heat. Mercury shows us the violence of proximity, a world stripped down to metal and stone. These planets are warnings written in orbits. If Earth listens, it will hear their stories, how climates collapse, how atmospheres die, how small changes create enormous consequences. The inner planets remember catastrophe so that we may avoid it. The giant planets, our protectors and teachers. Jupiter shields us. Saturn sculpts the outer system. Uranus and Neptune show us the diversity of worlds that can exist. They remember the collisions that shaped them, the storms that never cease, the migrations that could have destroyed Earth, the moons that may hold life of their own. We study them not only out of curiosity, but because our existence depends on their gravity. The giants watch over us, even if we never thank them. The Kuiper Belt and Oort cloud, the archives of what came before. The solar system stores its earliest memories in ice. Comets, Pluto, Arakoth, thousands of frozen worlds. These bodies carry chemistry older than Earth. They preserve what the solar system was, before the planets existed. Every time a comet falls inward, it brings us a message from the beginning, a whisper of our origins. The machines we sent into the dark. For billions of years, nothing left the solar system. Then humans built machines, and the solar system gained messengers. Voyager, Pioneer, New Horizons. They carry our voices, our music, our greetings, our diagrams, our dreams. The solar system remembers these probes as the first children of Earth to leave home. What the solar system remembers about humanity, not our wars, not our politics, not our fleeting troubles. When the solar system looks back at humanity, it remembers something else entirely. That we were curious, that we explored, that we learned, that we tried to understand. It remembers the first telescope, the first rocket, the first rover wheel pressing into Martian soil, the first spacecraft passing the heliopause, the first image of Earth rising above the moon's horizon, the first human who looked up and wondered. It remembers the questions that shaped our species. Where did we come from? What else is out there? What will we become? These questions are written in every mission we launched, every probe we sent, every observation we made. The future memory. One day, long after our generation is gone, long after our cities crumble, long after continents shift again, humanity's descendants may stand on other worlds, walking beneath Titan's orange sky, floating above Europa's cracking ice, diving into Enceladus's plumes, building cities on Mars, sailing methane seas, exploring the dwarf planets, touching comets with bare hands in magnetic gloves. The solar system will remember us, not by our limitations, but by our ambitions, by the fact that we refuse to remain small. And when we are gone, even if humanity disappears someday, our probes will remain. Voyager will still drift between the stars. New Horizons will still wander the Kuiper Belt. Echoes of our radio waves will still expand across the galaxy. Footprints will still lie undisturbed on the moon. The solar system will remember that once in the long quiet of cosmic time, there existed a species that dreamed, and that dream became its memory.